Hi everyone, this is Chen Feng from Primary University of London. I'm going to introduce our work titled MaskCon, Masked Contrastive Learning for Coarse-Labelled Dataset. In this work, we propose a contrastive learning method to deal with an underexplored weakly supervised problem. That is, we learn with a coarse-labelled dataset in order to address a final labeling problem. By contrast to self-supervised contrastive learning relying on instance discrimination tasks, and supervised contrastive learning relying on only coarse labels, we propose soft labels based on intersample relations, which are further masked by the coarse labels. We demonstrate that our method can obtain as special cases many existing state-of-the-art works and that it provides tighter bound on the generalization error. Experimentally, our method achieves significant improvement over the current state-of-the-art in various datasets. Let's start with the motivation. Unlike common supervised learning, in most real-world applications, the accurate annotation of large-scale datasets is often costly and difficult. For example, we want to classify different animal species. However, it is hard to tell between different categories for a non-expert. This is the focus of this work, that is, to learn with coarse-labelled dataset, but to address a final labeling problem. First, directly utilizing the coarse labels will lead us to greatly about the intersample relations, thus to ignore the interclass differences. A prevalent representation method now is to utilize the instance discrimination task, often known as self-supervised contrastive learning, which consider each sample itself as a unique class. This method, by contrast, being too conservative or too greedy, a straightforward solution is to combine these two ideas, thus to serve as a counter effect. Previous works actually followed this combination idea, for example, the cones and the graphics. However, it is unreasonable to equally reweight samples from the same coarse class. In this work, we aim to focus on those samples, more possibly from the same fine class, while ignore those false positive samples from other fine classes. We first briefly introduce the contrastive learning framework. Let us denote with X and Y the training dataset with coarse labels. In contrastive learning, we aim to learn the given intersample relations that, with a model encoder F and projector H, we first generate the projection of each sample Xi as Hi, and then calculate the cosine similarity and the predicted intersample relations Qi. Here, the tau serves as a temperature. We then have the contrast loss, which is similar to closed entropy loss in format. Thus, the core here is how to get a correct intersample relations Zi for learning. The most simple condition is we only consider each sample itself as a positive match, which is the self-supervised contrastive learning. As we can see, we only have one entry as 1 here and all others have been assigned as 0. When we have coarse labels, we can also consider samples belong to the same coarse class as positive. This is the recently proposed supervised contrastive learning. As we can see, we have multiple entries as 1 now. It is clear that compared to the ground truth intersample relations generated with fine labels, both the self-supervised one and supervised coarse one are suboptimal. We thus propose MaskCon. For example, we can get the I here, which is more close to the ground truth one. More specifically, we first generate an auxiliary view of sample xi denoted as x prime I. This can be easily done with any applicable augmentation strategy such as image cropping. Then we get its projective representation using the same encoder and projector. With this auxiliary view, we want to estimate the sample xi's relation to other samples. Thus, we calculate a similar cosine similarity to all other samples, but excluding itself. With this cosine similarity with respect to all other samples, we further introduce the coarse labels as a mask and calculate a sharpened Z prime. Here we use a different temperature tau. To be consistent with previous works, we apply a weighted scheme to balance the proposed soft labels and the hard label based on instant discrimination task. We also theoretically prove that MaskCon is better than utilizing the coarse label or self-label only, since it can reduce the generalization error. I will introduce some datasets applied in this work. We first use CVPR dataset. Specifically for CVPR10 dataset, we artificially generate two subsets by grouping 4 fine classes into coarse class. For CVPR100 dataset, we directly apply the original subclass labels as coarse labels. For ImageNet 1K dataset, we follow the WordNet hierarchy to group 1,000 fine classes into 12 coarse classes. For Stanford Cars dataset, we manually group 196 different car models into 8 coarse classes based on the widely acknowledged car types. For Stanford Online Products dataset, we have 2 different subsets. For split 1, we follow in the setting of image retrieval task. We select all fine classes with more than 8 images and evenly split it into train and test set. For split 2, we select all fine classes with 12 images and select 10 images as training, while remaining 2 images as test. Here we show some results on aforementioned dataset. In the common classification dataset, our method achieves significant improvement over baseline method and previous works. Especially, our method's performance approaches the results when you directly train with fine-grained labels. We also showed the testing visualization of learned representations on CVPR toy dataset. It's clear that our method achieved more distinct clusters and more clear boundaries between different classes. Here we show some results on more fine-grained dataset. Our method also achieved the best results in comparison with previous works. However, we also noticed that the best result we achieve here still has a great gap with the results get from training with fine-grained labels. Here we show some visual examples of image retrieval results in CARS 196 dataset. As you can see, our method can effectively identify correct neighbors with different car models and types, which shows our method is quite robust. To summarize, we propose an efficient contrastive learning framework for the underexplored problem, and we also manually generate coarse labels for several datasets. We expect our work can serve as a strong baseline and motivate more works to deal with this problem. Please refer to our paper and code for more details. Thank you.